Okay, now we are on to video lecture 19. We are on to video lecture 19 now. And now I will introduce you to a topic which is very interesting. Because our topic for this lecture and possibly for a part of the next lecture is characterizing a metamorphic fluid. Now I have told you before, that metamorphic fluids normally occur in the system COH. Metamorphic fluids, remember fluids. These can be over 99% could be characterized for the system COH. And these fluids are in equilibrium with the mineral assemblages. Like, for example, I showed you in the lecture before, some of the lectures before, that from mineral assemblages we can write different things, phase component, system component, independent reactions, and then we can retrieve pressures, we can retrieve temperature, we can retrieve XH2O, XO2, sometimes XCO2. But we cannot determine everything. But we can determine parts of the fluid composition without going into the generalization, whether there is a fluid presence situation, whether there is a fluid absence situation, no. But we can find out the mole fractions of some of the fluid components. Now, so these, if we assume that you have a COH fluid, which is in equilibrium with the mineral assemblage, then there is constant communion between, so the materials that you, so the parameters, intensive variables that you determine for the mineral assemblages are equally applicable to the fluids, which you can deal separately. So, because sometimes, as you have seen when I took your class test, that degrees of freedom can be very high, mineral assemblages can be long, they can be very cumbersome to handle, and if you add COH to the system, then the whole system becomes so complicated that it becomes very difficult to really model metamorphic phase equilibrium. So sometimes what we do is, we assume that there is a rock and you have certain minerals in it, and have certain minerals in it, A, B, C, etc., in it, and you have a reservoir of fluid, and you have this mineral is in equilibrium with the fluid. So therefore, from this mineral assemblages, the metamorphic intensive variables that we can find, say for example, commonly pressure, temperature, sometimes XH2O, sometimes XO2, sometimes XCO2, depending upon the mineral assemblages. Not all assemblages give everything, but some of these can be found out from the mineral assemblages by modeling the mineral assemblages. And these input variables that you determine from the assemblages, these also are relevant to the fluid composition which is in the COH system. So these can be added as inputs for computation of fluid compositions. Right? This is the basic idea. That if you have a fluid in equilibrium with a mineral assemblage, and if we can find out for a particular equilibrium pressure, temperature, mole fractions of certain compounds, fluid compounds, then we can take this and apply it to the COH fluid to retrieve some more data. The question is, what is the other data? So I want to stress on this point that from the mineral assemblage you can derive intensive variables. And these intensive variables can be used as input for estimating fluid components that you have not yet characterized, but they are also equally very important. This we can do. Let's take it that yes, we can do this. So now, what we can do, we can take this whole system and break it up into whole system and break it up. This is one subsystem and this is another subsystem. So we have taken this system and we have found out certain parameters by using the mineral composition data, etc. We have gone through all this, so I don't have to repeat it. But we can also take the fluids as a separate entity and treat it as a fluid component, and we can take the inputs from here to compute more metamorphic variables related to the equilibrium. And my focus for this class and for a part of the next class would be to emphasize on this very important thing. So my things will be that I will be talking of the COH system, but remembering that this COH fluid is in equilibrium with a mineral assemblage from which data, thermodynamic data, can be retrieved using the compositions of the minerals which are determined from using electron microprobe data. Right? This would be my effort to tell you. And this leads to certain very interesting questions. Now, before we go, I would like to tell you that this fluid, whether you have a fluid present condition or a fluid absent condition, but the relationship or the mixing of the different fluid components, phase components in the fluids, we take them as ideal. We take this mixing in the fluid as ideal. It's not ideal. It's non-ideal. But we take it as an ideal. Why? Because it makes the computation simple. And as I have always stated, that it's easier for you to look through the equation and see what's really going on. Activity, if you use instead of mole fractions, which is ideal, if you use activities, the complication comes from the gamma terms. And as you know, these gamma terms are not only functions of compositions, but also functions of pressure and temperature. So it makes it a little complicated. So it makes the equation more cumbersome to handle, and you really get lost a bit in the different numbers and parameters that you have. You get completely lost in it, and you don't see the central point of the logic. So I will assume ideal mixing among all the fluid, all the phase components within the fluid. Right. So we come to this COH system. The important part in this system is the COH system. You know, it's a huge system. It's the system which includes everything in organic chemistry, except for potassium, nitrogen, and other things. It takes in everything from organic chemistry. Alcohol, alkenes, alkanes, all that you know, acetic acid, everything comes under it. But from natural phenomena, natural evidences, what we see is the fluids in the Earth's crust and in the Earth's mantle, which we can access, and that's not much, just about 400, 500, 600, 700 kilometers at the most. Below that, we almost have no control. In that fluid, these are the following fluid components. Say, for example, H2O, CO2, CO, CH4, H2, and O2. These are the fluid components, the components or the phase component of a fluid. This, say for example, methane, CH4, say for example, all these components vary with depth, vary from rheology to rheology, so none of them have a consistent thing, although we know that, you know, if you have oxidizing conditions, then you will have carbon dioxide. If you have reducing conditions, you will have carbon monoxide. So, say for example, if you talk about the mantle, there should be a home for methane, which is otherwise not really present in crustal rocks. So, These vary with rocks and with depth from the crust to the mantle. So these are the fluid components. And once again, we have therefore sigma xi fluid equal to 1. That's fluid present. That means XCO2 plus XH2O plus XCO2 plus XCO plus XO2 plus XH2 equal to 1. That is the idea of fluid present metamorphism. But for fluid absent metamorphism, sigma xi in the fluid is not equal to 1. And that is what is called fluid absent. And the rule for that is not equal to 1. So basically, what is the difference between fluid present and fluid absent? The difference is, if these are added up equal to 1, it's an equation. For fluid absent, you lose an equation because they do not add up to 1. So it is a situation where you lose an equation. Fundamentally, this is the most important point, that you lose an equation. So for this COH, you can treat it as fluid present system, which would mean the summation of all this is equal to 1. Or you can have it as a fluid absent situation, where summation xi fluid is not equal to 1, which means you lose this equation. Remember, losing an equation is a big, big thing. By now, I think you must have understood from your study of variance, etc. Losing an equation is a big loss. It's a big, big loss. Right. Now, so we can have fluid present and fluid absent situation, and these are the fluid components, or the phase components in fluid. There is also another important aspect of this system. You must realize that two minerals, graphite and diamond, both having the formula C, are also a part of this system. So if you take the COH system, you can have graphite and you can have diamond. So either you can have graphite, or you can have diamond, or you can have graphite and diamond, or you can have none. Your rock does not contain either graphite or diamond. So either, once again, you will have graphite at low pressure, crustal conditions. Uppermost mantle, you may not have diamond, but as you go deeper into the mantle, you're expected to get diamonds. Right? But you can also go through the graphite diamond transition pressure, where you will see both of them in equilibrium. Or, in the rock composition is such that neither graphite nor diamond is present. You can have both situations. I think since we are doing this, we are not really talking of mantle petrology at the moment. We will, for our discussion for this class, essentially very related to crustal metamorphism, we can ignore this. But if you're dealing with the mantle rocks, you have to be very sure about the presence of graphite and diamond in equilibrium. But for us, we are taking it, say, in the crustal rocks as well as in the higher uppermost mantle where diamond is not stable. Right. So when you say you can have two situations, graphite present, which would mean activity of carbon in graphite is equal to 1, or ideal writing is equal to 1. And graphite absent, you can have this situation, absent, where activity of carbon in graphite is less than 1. Similarly, if we do ideal things, then this is equal to 1. Once again, just like your fluid present and fluid absent, activity of graphite is equal to 1 is an equation. Or Xc in graphite equal to 1 is an equation. But when you say graphite absent, you lose the equation. Just like you lost it when you had fluid absent conditions. Same thing, same logic. There's no shift in the logic, no manipulation here. So, you can have assemblages, COH system assemblages, where you have graphite in the rock, or you may have no graphite in the rock. If you have no graphite in the rock, then graphite is absent. That means activity of carbon in graphite or Xc in graphite has to be determined. It's unknown if it's absent. If graphite is absent, it means the mole fraction of carbon in graphite is not known. But if you take graphite is present and the activity of carbon in graphite is equal to 1, it's known. So if we take this, then something interesting comes out. We can have, remember these are the phase components. We can have several situations, several cases can come in. Let's say case 1, which appears to you will appear it to be comfortable with it. We are dealing with a system where fluid is present and graphite present. That means we can have this case. Fluid present, graphite present. That means sigma xi in the fluid equal to 1. Activity of graphite, carbon in graphite equal to 1. Right? Or you could have fluid present, graphite absent. So you have a COH fluid system where you have a fluid present situation, sigma xi equal to 1. But activity of carbon in graphite is not equal to 1. We can have this situation as well. And we can take case 3 where you have fluid absent, graphite present. Fluid absent, sigma xi fluid is less than 1, but graphite is present. Activity of C equal to 1. Or you can have case 4, which appears very funny. Fluid absent, graphite absent. This looks funny. You have a COH system, there is no fluid, and there is no graphite. There is no fluid, there is no graphite. Strange, isn't it? But it can be dealt very easily. In fact, this is the easiest. But we need to address this situation. We need to address this situation. This class, I will talk to you about fluid present, graphite present. And I will ask you to work on these two. I will maybe show you one of this, and the other 2, 3 and 4, you can do it. So I will start with case 1. So, remember, since I don't keep any notes, if I write 3 as 2 in the next class, please don't mind. It doesn't matter. The three cases should be there. So we have fluid present, graphite present situation. So it's interesting. So first of all, we go back to the Gibbs phase rule. F is equal to C minus P plus 2. How many components? 3. How many phases? Both are present as phases. Minus 2 plus 2 is equal to degree of freedom 3. Degree of freedom 3. Now, remember, when I started, I said this fluid is in equilibrium with the mineral assemblage. And normally for mineral assemblage, we know pressure, temperature at least. So if we know pressure, temperature, then the Gibbs phase rule says, what? That means, what does it say? That's very interesting. What does it say? What are the variables here? Okay, before you go into this, F is 1, right? At the pressure temperature control. Right. What are the metamorphic variables? Metamorphic variables involved in the COH system? I will write it. Pressure, temperature. This is for the fluid. XH2O, XCO2, XCO, XCH4, XH2, XO2 and XCA graphite. These are the intensive variables involving the COH system, for which pressure and temperature are known because we can get it from the mineralogy of the rock. And we know this value. What is the value? The value is 1 because graphite is present. So if graphite is present, this value is known. So now, if we look at this, what does it tell you, the Gibbs phase rule? The Gibbs phase rule says at a known pressure and temperature, one intensive variable needs to be input into the system. To do what? What? To do what? To do what? What shit are you going to do? Are we going to do with it? What are the variables? One variable needs to be an input. And how many variables do you have? 1, 2, 3, 4, 5, 6 variables. You need 6 variables. Temperature and activity graphite are known by definition. So you have XH2O, XCO2, XCO, XCH4, XH2, X2. There are 6 variables left to be found out. And the Gibbs phase rule says only one would do. If you put one value, I will give you the rest 5. And you wonder, how is it happening? How is it happening that I put in one intensive variable here, and there are 6 of them here, and I don't need anything else? Strange. And slowly you delve deeper. And you ask yourself, how does it say one variable? Okay, let me do one thing. Let's say I take XO2. This is input from the rock, remember? From the mineral assemblages we could find out XH2O or XCO2 or whatever that is we could find out. Let's say my input variable is XO2. I still then have 5 variables left. How can this be? So, Gibbs phase rule says at a constant pressure and temperature, and for graphite present situation, one input variable is needed, and I say, okay, let my variable be XO2 and XO2, and I'm left with 5 variables. How is it possible to have 5 variables? Then you ask yourself, okay, let me see. I have some independent reactions. Let me go into that process. Let me see how many independent reactions I will have. 5 of them, and I have how many independent reactions? So you start. independent reactions, phase component minus system component. How many are the phase components? 1, 2, 3, 4, 5, 6, 7. 7 phase components. So this essentially 7 minus 3 is equal to 4. There you go. So there are 4 reactions. So there are 4 independent reactions. Input variable was O2, but this says you have 4 independent reactions. 4 independent reactions. And I sit down and wonder what's happening. 4 independent reactions. Should I try to write? Let me write. Okay, let me start somewhere. I will start it from here. C plus O2 is equal to CO2. Independent reaction A. Right? C plus half O2. CO. Reaction B. I can't have more than 4. I have reached 3. C plus 2H2. CH4. C. O2 plus H2 is equal to H2O. D. 4 reactions. So now, let's go back. We stop here. We stop here. The logic is important. We stop here. Right. Where did we start with? 1 input variable at a known pressure, temperature, and X graphite is 1. So I took 1 input variable. I'm left with 5 variables. So if I have to have 5, I need to have 5 equations. But independent reactions that I can have is maximum 4. I will not have 5. And there I am stuck. I have nothing else. I have nothing else. I don't have anything with me. I have consumed everything. I have consumed the Gibbs phase rule. Tells me 1 input variable. I use this input variable. It says independent reaction should be 4. I have written down 4. And still there are 1, 2, 3, 4, 5. Not O2. O2 is already an input. 5 variables and I have 4 reactions. And then I scratch my head and I think, do I have a reaction somewhere? Do I have a reaction somewhere? And suddenly it occurs, yes, I have. I have. What is it? XCO2 plus XCO plus XCH4 plus XH2O plus XH2 plus XO2 is equal to 1. Fully present. Now you are feeling a little bit more comfortable. Now you are feeling a little more comfortable. What is the comfort? That you have 4 independent reactions, 1 equation from the definition, and you have 5 variables. And then you breathe and tell yourself, okay, so some hope. 5 variables, 5 equation is fine. That I can handle. And now you start doing, what then am I going to do? So then you write, then you say, how, and out of this, remember, XO2 is used as an input. XO2 is used as an input. Right? It is used as an input from Gibbs phase rule. I assume that I can bring in that value into my calculations from the mineral assemblage, with which this COH fluid and is in equilibrium with graphite. That means graphite is a part of the mineral assemblage. Right. So now you have XO2. And suddenly I look at reaction A. How do I write reaction A? I'm writing this. You please see. You can write it. XCO2 in the fluid is equal to this is how reaction will go. This is how reaction will go. Important point here. How did I do? Again, I don't want to write it. It's the same. What is del G0? I will just tell you once so that you may have forgotten. What is del G0? A is equal to del H0A minus T del S0A plus P del V0A and then plus RT, your del G, this is del GA. Have you understood? Plus, so this is del G0A. So, have you understood? So, I don't have to repeat. Del G0A is equal to del H0A minus T del S0A plus P del V0A. Now, if you know pressure and temperature, this is a constant. At known pressure temperature condition, this is a constant. And Xc in graphite is 1. So this is known, and only this is also known as input. Have you understood? This is known, Xc graphite present. The number is known. XO2, I have taken it as an input. I know this value. And this value is a constant at pressure temperature condition, which I retrieved from the minerals. So this value is constant. So I can find XCO2. I can find from reaction A, XCO2, which means now this is determined. So XCO2, I took it as input, circle. And now I have found this one. I have found out XCO2 using reaction A. Now you see, for reaction B, it will be the same. In fluid is equal to, now you see here, Xc in graphite into XO2 to the power half into exponential into minus, I have forgotten, exponential is, sorry. There is an RT missing here. Sorry. This was missing, I'm sorry. And here, it's minus 1 by RT into delta G0B. There you go. So, look at this again. At a particular temperature of equilibrium, this value is a constant. Xc graphite is equal to 1. XO2 is an input. So, XCO can be determined. So, I have this can be determined. So, this is determined, this is determined. This was used as an input. Now the problem is with these three. And you have 3 and you have 2 reactions. So now you see what happens to this. From C what you get is XCH4 is equal to, I'm omitting this because you see graphite, I will write it anyway, Xc graphite into XH2 whole square into exponential minus 1 by RT into delta G0C. But I can't find a value for XCH4. I can't find the value for XCH4. This is 1, no problem. This is 1, no problem. This value is a constant. Right? This value is a constant. But this value, I don't know. So, how do I write this expression? I write this expression as, I erase this, and for this I write K3. Do you see? I write K3. Because at the equilibrium, K3, or not K3, Kc. Kc. Kc is the constant of this at a particular temperature. So 6HCH4 can be written in terms of Kc into XH2. Now you see here. Now I write. So just before I switch over, from A and B, I found out XCO2 from A. I found out XCO from B. Right? So XCO2 and XCO from XC and B. The rest I have not found out still. I am still finding that, and this was used as an input. Now I write for reaction D. What will I write? H2O XH2O is equal to XO2 to the power half into XH2 into exponential minus 1 by half t into delta G0 D. That's the expression for D. Now this is interesting. Now look at this. This is known. XO2 is known because we took it as input. So this value is known. And this value, because we know the pressure temperature condition from the mineral assemblage, this value is known. Right? So this expression now we can write as this is how we can write it. So that's the important point now. So we have not yet been able to find out H2O, H2, CH4 and H2. We have not been able to find out. But what we have done is an interesting thing. We have written CH4 in terms of XH2. We have written XCH4 in terms of XH2. We have written XH2O in terms of XH2. Have you understood? So, if I now change this equation to the left and the right, let me write it, you will get it then. So, I can write the expression as XH2O plus XH2 plus XCH4 is equal to 1 minus XO2 plus XCO2 plus XCO. Do you see that? I can write this. What I have done, the unknowns I have brought it to the left, knowns I have taken to the right. Remember, 1, 2, 3. 1, 2, and 3. These are known. And I can write this expression a little differently. I can write now XH2. So now I can write XH2O. So I can write this in terms of this. So I will write KD into XH2 into XO2 to the power half. This is for XH2 plus XH2, of course, plus, now for CH4 I can write Kc into XH2 whole square. And this will be equal to 1 minus XO2 plus XCO2 plus XCO. Okay, so now I will erase this part. Yes, I will erase this part. If there is any mistake, please let me know. Sometimes I do make mistakes, but nothing that you will not be able to discover. So now what we have is, yes. So now I will rearrange these two terms. So I will write XH2 into XH2 whole square into, I will write it slightly differently. So that term is here. These two terms have both XH2. So I will write here plus and then KD into XO2 to the power half plus 1 is equal to XH2. So see, I have taken out XH2, I have written KD XO to the power half plus 1 because that is what remains here. And so I have taken care of this term, I've taken care of this term, I've taken care of this term. And now I write plus bracket XCO2 plus XCO plus XO2 minus 1 is equal to 0. I have just brought this to the left hand side, so the sign changes. Now I will write AX square plus BX plus C is equal to 0. Do you see that? This is a quadratic equation in XH2. This is a quadratic equation in where XH2, your X square is essentially XH2 square, XH2. So KC is like A, B is this one, and this is C. So essentially, it will have two roots. Yes? So you know the root? So you know the quadratic equation has two roots. Both may be real, Both may be unreal or one real and one unreal. So all the unreal values, if you solve this equation now, the unreal values cannot be the mole fraction values, because mole fraction values will lie, XH2 for example, has to lie between 0 and 1, nowhere else. Between 0 and 1. And any other value for XH2 is wrong. So we have one constraint there. So if you get two solutions, two real solutions, root over b square minus 4ac divided by 2a minus b plus minus root over b square minus 4ac by 2a, that famous equation which you did in school. So if you have XH2 values outside 0 to 1, they are wrong. Also, if you have XH2 value which are unreal, that means root of minus, they are wrong. So you take only those that are real, 0 and 1. So this will give you a value for XH2. Have you understood? This will give you a value for XH2. So now you find out XH2. Have you understood? So if you found out XH2, now you can also find out XCH4. If you look at reaction C, so this is essentially XCH4. So essentially, if you know XH2 now, Kc into XH2, and you will get XCH4. And if you take reaction D, which is this one, you know XO2, you know Kd because of pressure temperature, and you know XH2, then you also know XH2O, of course, because XH2O was equal to Kd into XH2 into x to the power half, etc. So if you know XO2, you now know XH2, and you now know Kd, therefore you can also find out what was XH2O. So there you go. You found out all the parameters that are necessary for your computation. All parameters that are necessary for computation. Gibbs phase rule saw it early. Gibbs phase rule saw it early. So now, you have this solution to fluid present and graphite present solution, that you have the degree of freedom actually is free. For at pressure temperature condition which is known, the Gibbs free value is isothermal isobaric degree of freedom is 1. So it says if you give me one input variable from the minerals, I can compute all the parameters. This is already known because graphite is absent. These two are already known from thermogrammetry. So it says if you give one parameter, I will give you all 6 parameters. Why? Because there are 4 independent reactions. It doesn't matter how you write the reactions. There are 4 independent reactions. And which is inherent for the system. And you have one extra equation. And that extra equation is summation xy is equal to 1, because that is for fluid present situation. If you do that, then as I have shown you, you can solve it, and if you use this input, you can use another input and try the calculation yourself. Change the independent reactions, try it yourself. If you can work with another input, CH4, that will be a good test for you. Right? So this is how, using, we were pressure temperature, and then we were trying to find out XH2O, O2. Why? Why were we trying to find out those? Because we know that those input value we will use in completely characterizing the COH system. The full COH system we will be able to characterize if I can find out as many variables as possible. Right? So that is very important. Now this is the case 1, which is fluid present, graphite present situation. I think what I will ask you to do is, this is video lecture 19, I think. You do one thing. I will prepare another video lecture and I will keep it with me. I will post it midweek later, sometimes. So in that time, you try to take the cue from here and try to see if you can use another input to do your equation, but it has to be correct thermodynamically. And then you try case 2. I did case 1 only, so you try case 2 and case 3. I will just give you a clue for case 2. This is, I am erasing. I don't remember what I wrote as x2. Case 2, I think I wrote, I don't know. I can't tell you. I don't know. Let's do it. Let's do 1. Okay. Let us look at this. Graphite absent. This is, I think, case 2. It does not matter. We have 4 cases. We can deal with it. Fluid present, graphite absent. Right? Now, but we know that pressure, temperature, etc., all these things we can control from the mineral acid relationship. So now here, last time, when it was fluid present, graphite present, we took activity C graphite, the value was determined. Why? Because it was pure. But then Xc graphite is equal to 1. Here, of course, that advantage you don't have because you have graphite absent. So that advantage is gone from you. That advantage is gone from you. It has now become an unknown. It has Xc graphite has now become an unknown. So graphite is not a part of the system. Graphite is not present. So Xc graphite is unknown. But sigma Xi fluid equal to 1, that equation remains. That equation remains. So XCO, XH2 plus XCO2 plus XCO plus CH4 plus H2 plus O2 equal to 1. That remains because it's fully present. Now, so F is equal to C minus P plus 2. Now, what is C? Well, obviously C is 3. And now phase. One phase. Fluid present. Graphite is not present, so it's not a phase. So, 3 minus 1 plus 2. So that is 4. At a known pressure temperature, 2 input variables are necessary. That's what it says. 2 input variables are necessary. That's what it says. The equation says so. You have to input 2 variables. So now if you input 2 variables, so I don't know which variables, let's say, we take, doesn't matter. We take this and this. These are the 2 input variables. So it means 1, 2, 3, 4, 5, there are 5 variables left. We take these 2, then 1, 2, 3, 4, 5 variables are left. How many independent reactions do we have? Independent reactions. Phase component minus system component. How many other phase components? 1, 2, 3, 4, 5, 6, 7. Same 7. System component 3. Again, independent reaction is 4. So you have 4 independent reactions and you have this reaction in your pocket. You have this in your pocket already. So you have 5 variables which can be solved by 4 independent reactions and 1 equation by definition. Right? So I will suggest to you that you try all combinations to find out all the 4 cases. Yes? all the 4 cases. And I will do the video lecture today, and I will post it sometime later in the next week. So you will be able to see whether you get it, right? But I will ask you to do it before, say, Wednesday. So I upload it on, say, Thursday, so that you can check out whether you did the right thing or the wrong thing. And remember, this 1, 2, 3, 4, you can forget about it. I just wrote because 4 cases. It does not matter if this is 3 or 2 or 4. It doesn't matter. Right? Fine. Thank you.